Hello everyone. This presentation is about image enhancement in spatial domain. The contents of this presentation are: first, introduction, in which we will see categories of image enhancement methods. Then, gray level transformations. We are going to see various gray level transformations, that is image negatives, log transformations, and power law transformations. We'll start with the introduction. The main objective of enhancement is to process an image so that the result is more suitable than the original image for a specific application. Image enhancement approaches fall into two broad categories. The first one is spatial domain methods and the second is frequency domain methods. The term spatial domain refers to the image plane itself, and approaches in this category are based on the direct manipulation of pixels in an image. Frequency domain processing techniques are based on modifying the Fourier transform of an image. Spatial domain refers to the aggregate of pixels composing an image. Spatial domain methods are procedures that operate directly on these pixels. Spatial domain processes will be denoted by the expression g of xy is equal to t of f of xy, where f of xy is the input image, g of xy is the processed image, and t is an operator on f defined over some neighborhood of xy. In addition, T can operate on a set of input images, such as performing the pixel by pixel sum of k images for noise reduction. The simplest form of T is when the neighborhood is of size 1 by 1, that is a single pixel. In this case, G depends only on the value of f at xy, and T becomes a gray level transformation function of the form S is equal to T of R, where R and S are variables denoting gray levels of f of xy and g of xy at any point xy. The general approach is to use a function of the values of f in a predefined neighborhood of xy to determine the value of g at xy. One of the principal approaches in this formulation is based on the use of so-called masks or filters or kernels or templates or windows. A mask is a small, for example 3 by 3 two-dimensional array as shown in this figure. In this approach, the values of the mask coefficients determine the nature of the process, such as image sharpening. Enhancement techniques based on this type of approach are often referred as mask processing or filtering. The center of the subimage is moved from pixel to pixel starting at the top left corner. The operator T is applied at each location xy to yield the output G at that location. The simplest form of T is when the neighborhood is of size 1 by 1, that is a single pixel. Now we will see gray level transformations. The values of pixels before and after processing will be denoted by R and S respectively. These values are related by an expression of the form S is equal to T of R, where T is a transformation that maps a pixel value R into a pixel value S. The figure on the next slide shows three basic types of gray level transformations used frequently for image enhancement. The first one is linear or negative and identity transformations. Number two, logarithmic, that is log and inverse log transformations. And number three is power law, that is nth power and nth root transformation.
As said in the previous slide, this figure shows basic gray level transformation functions used for image enhancement. Here in this figure, x-axis shows the input gray level value, that is value of R, and on the y-axis there is output gray level value, that is value of S. First, image negatives. The negative of an image with gray levels in the range 0 to L-1 is obtained by using the negative transformation as shown in figure 2. This is given by the expression S is equal to L minus 1 minus R. Reversing the intensity levels of an image in this manner produces the equivalent of a photographic negative. This type of processing is particularly suited for enhancing white or gray detail embedded in dark regions of an image, especially when the black areas are dominant in size. Log transformations. The general form of the log transformation is S is equal to C into log of 1 plus R, where C is a constant and it is assumed that R is greater than or equal to 0. This transformation maps a narrow range of low gray level values in the input image into a wider range of output levels. The opposite is true for higher values of input pixels. Transformations of this type is used to expand the values of dark pixels in an image while compressing the higher level values. The opposite is true of the inverse log transformation. The log function has the important characteristic that it compresses the dynamic range of images with large variations in pixel values. Power law transformation. This transformation have the basic form S is equal to C into R raised to gamma, where C and gamma are positive constants. Sometimes this equation is written as S is equal to C into R plus epsilon raised to gamma to account for offset, that is a measurable output when the input is 0. Plots of S versus R for various values of gamma are shown in this figure 3. As in the case of log transformation, power law curves with fractional values of gamma map a narrow range of dark input values in a wider range of output values, with the opposite being true for higher values of input levels. A variety of devices used for image capture, printing, and display respond according to a power law. The exponent in the power law equation is referred to as gamma. The process used to correct this power law response phenomena is called gamma correction. For example, CRT devices have a intensity to voltage response, that is a power function, with exponents varying from approximately 1.8 to 2.5. With reference to the curve for gamma equal to 2.5 in figure 3, we see that such display systems would tend to produce images that are darker than intended. Gamma correction is important if displaying an image accurately on a computer screen is of concern. Images that are not corrected properly can look either bleached out or too dark. Trying to reproduce colors accurately also requires some knowledge of gamma correction, because varying the value of gamma correction changes not only the brightness but also the ratios of red to green to blue. Gamma correction has become increasingly important in the past few years as use of digital images for commercial purposes over the internet has increased. That's the end of this presentation. Thank you.